In this lecture, we're going to cover Chapter 17, Section 4, and look at acid-base titrations, where we have both a strong acid and a strong base. So I wanted to point out just an item in the study guide from Chapter 17, where I have notes on acid-base titrations. And so please make sure you have this downloaded on your computer, printed out. So a couple of definitions to go over with. A definition of the equivalence point of a titration. And this is that the moles of acid in the beaker equal the moles of base added from the burette. Or if you have base in your beaker, the moles of base in the beaker equal the moles of acid added from the burette. And the key here is moles. So moles of acid equal moles of base, not molarity, moles. And the topic that we're going to look at right now in this video, strong acid, strong base titration. So what we're looking at, we have, in this example, our strong acid HCl, strong base NaOH. So looking at our double displacement reactions that we learn in Chem 60, Chem 101, we are going to produce water and a salt. And the definition of equivalence point means the only thing in your beaker at the equivalence point are products. So the products here are going to be pH neutral, or pH of 7, because water, we know, has a pH of 7, and NaCl, sodium and chloride, we know neither of these affect the pH, right? The cations of the strong bases don't affect the pH, meaning they just hang out in water, pH stays 7, and the same with the anions of the strong acids. So this will be the topic for today, strong acid, strong base titrations, and I'm just starting with a definition of equivalence point and reminding you of what we have in our study guide. So here is an example of an acid-base titration. We can see that we've got a strong acid in our beaker, right, HCl. We have strong base in the burette, NaOH. We learned to use burettes in Chem 60 and Chem 101. We'll be using them again in 102. And here this is a pH meter. So the pH meter actually reads the exact pH with this electrode that's submerged in the solution. So in this case, we have HCl in the beaker with a pH of 1.30. So the pH is less than 7. That makes sense since we've got acid in our beaker. So this is an example of a setup for an acid-base titration. Now we're looking at a titration of a strong acid with a strong base, and we're looking at the graph. So a couple things to think about. When you look at a graph, the first thing I want you to look at are, number one, the title, so we can see titration of a strong acid with a strong base. Number two, your X and Y axes labels. So I can see that I've got milliliters of NaOH on X. That means that you are adding your strong base, which is NaOH, from the burette. Right, so it's coming from the burette, and you know that because you can see the different milliliter readings as you're adding that. And then on the y-axis, in this case, we have pH. So we're measuring the pH of the solution in the beaker as we add NaOH from the burette. And I know that the solution in my beaker is an acid because my initial pH, so which is right here, is low, below 7. That tells me I've got an acid in my beaker. And I can see when I have 0 mils of NaOH added, my pH is 1. So in this case, initially, what is in my beaker, HCl, the strong acid here, so if we were to have microscopic eyes, and that's exactly what we're drawing into that beaker. So we have H+, Cl-, and then there's always going to be water present because everything we're looking at is aqueous. And then what happens as I add NaOH from my burette, so what I have in here is NaOH. You can think of Na+, OH-, they're completely dissociated. So that reaction, as soon as I add any OH- from my burette, it's going to match up with the H+ in the beaker, and then we're going to create H2O, which is neutral. So as I add my NaOH, I'm going to be left with sodium cations that we see here. So my sodium cations are going to be in there along with the HCl. In this region, which we're looking at and calling before the equivalence point. So what I have in this zone is before the equivalence point. Remember our definition of equivalence point, right in the center, moles of NaOH added equal moles of HCl initially in beaker. So if I'm adding equal moles, that means I only have products left over. So NaOH aqueous plus HCl aqueous produces H2O liquid and NaCl aqueous. So at the equivalence point, we have only products in the beaker because you've added a 1-to-1 mole ratio of the reactants. And then, so this is our example of at the equivalence point. So what I have here are my sodium cations and my chloride anions. And of course, water. And then we call the zone beyond the equivalence point this region past the equivalence point. So what would that be? That means that you're adding more, right? More NaOH from the beaker. So what is in our beaker past the equivalence point? You've added excess base. So we have excess NaOH added, so we have some unreacted hydroxide. We've got our chloride still, and we've got sodium inside. So before the equivalence point, you have reactants present still. Past the equivalence point, you have whatever is being added from your burette just going into the beaker and hanging out. And then again, our definition of at the equivalence point, moles of acid and moles of base are equal, so we have only the products present. So for strong acid, strong base, that will always be a pH of 7 for the products at the equivalence point, because water is pH of 7 and the cation of a strong base and the anion of a strong acid are always pH neutral. Another thing I noticed, the shape of this curve. So we start out pretty flat, we shoot up really quickly, and then we curve out to a high pH. And I see my equivalence point pH is at 7. These are unique characteristics for strong acid, strong base titration. So let's go ahead now and look at practice exercise 5, pH calculation for strong acid, strong base titration. So the steps we're going to follow are identical to that of our buffer plus strong ACE acid or buffer plus strong base. So to remind you of those steps, number 1, write your reaction and calculate all moles. Number 2, IC end with moles, where you subtract and add smallest number. And then number 3, think what is in my beaker. So what we're looking at for this practice exercise 5, in part A, we'll do this one first. So calculate the pH when the following quantities of 0.1 molar HNO3 have been added to 25 mils of 0.1 molar potassium hydroxide, which is a strong base. And so for A, we're looking at 24.9 mils of the HNO3. So here I'm going to introduce you to using millimoles. So a millimole to a mole is the same thing that a milliliter is to a liter. So we know that there are 1,000 milliliters in 1 liter. There are 1,000 millimoles in 1 mole. So in part A, I know my strong acid HNO3, 24.9 milliliters times 0.100 molar gives me 2.49 millimoles of the acid. And that's just easier than using 2.49 times 10 to the negative third. It's just a very convenient number to use. Our base, KOH, strong base, I have 25.9 milliliters times 0.100 molar. Oh, excuse me, that's 25.0 equals 2.50 millimoles of KOH. So I started with my moles, and now we're going to write our reaction. So I know acid-base reaction. If I want to look at the complete molecular equation, so we're looking at just a double displacement reaction. So that's something you can review from your earlier chapters from Chem 101. So you swap your cations and anions. Also just our acid-base reaction to make water and the salt. In this case, the salt is KNO3. And I remember that potassium doesn't affect the pH. Nitrate also doesn't affect the pH. Now my IC end box with moles. So HNO3, 2.49 millimoles. My KOH, 2.50 millimoles. We're going to change sign underneath the arrow. Water doesn't count. No potassium nitrate to start with. The change, subtract the smallest number, so minus 2.49 millimoles. And again, really important to use units because we have to use moles or millimoles. We cannot use molarity. We're adding it to the other side because we use up reactants and make more products. So we use all of the HNO3, that's our limiting reactant. I have excess KOH, so 0.01 millimoles of KOH, and then I end up with 2.49 millimoles of KNO3. And so now step 3, stop and think, what is in my beaker at the end of this reaction? So at the end of this reaction, I have KNO3, and I know this is pH neutral, pH 7, so I can ignore that. But what I do have is KOH. Remember, KOH, this is a strong base. So how do I get the pH of a strong base? So stop and think. That's a strong base, so negative log of the molarity. So in this case, let's erase that. A POH is negative log of the OH minus molarity, which is negative log. Remember, now we need molarity, not just moles or millimoles. And a quick note, molarity is equal to moles of solute divided by liters of solution. It's also equal to millimoles over milliliters. So I can see how this is going to be convenient. So I have 0.01 millimoles hydroxide for every, and now what's the total volume in my beaker? So the total volume in my beaker at the end, well, I added my 25 mils of the base that was in the beaker plus 24.9 milliliters of the acid. So you add up the volume of the solution in your beaker plus the volume of solution you added from the burette. So I know I had 25.0 milliliters of the KOH that I added into my beaker to begin with, and then I added 24.9 mils of the acid from the burette. So now I can solve for a pOH, which I got as 3.699. And now I can calculate a pH, just equals 14.00 minus 3.699. So my pH equals 10.30. And this makes sense because in my beaker, I've got a basic solution. KOH is a strong base. So I expect to have a pH greater than 7. So quick recap. For all titration problems, this one specifically, we're looking at strong acid, strong base. You want to get the moles or millimoles of what's in your beaker. So we do that, milliliters times molarity gives me millimoles for the acid and the base. Write down your reaction, so important. So we're just looking at an acid-base reaction or a double displacement. IC end with moles. You have to remember to convert to moles because if you pour two different solutions in a beaker together, the concentration or the molarity will change. The moles do not. So initially I have the two reactants, no product. My change, I subtract the smallest number. We're essentially looking at a limiting reactant problem in the icebox, add it to the other side. At the end, you just add up your columns and then think what is in my beaker at the end. Well, my KNO3 doesn't affect the pH, so I ignore that. My KOH definitely does. It's a strong base. So then we have to think, how do I get the pH of a strong base? Well, first I get a pOH of the molarity. I get the molarity of the hydroxide by taking the millimoles that I added or that left at the end, divided by the total volume in your beaker at that point in time. So the milliliters of the base plus the milliliters of the acid that you added from your burette. And once you get a pOH, we can then subtract from 14 to get a pH. So go ahead and work on practice exercise 5 part B. Set that one up yourself and then go ahead and watch the next lecture video to check it out.